Prospect evaluation class. For today, we will discuss about reservoir evaluation to continue our previous discussion on drilling. It seems like here we are repeating the feasibility studies that we have done previously before the drilling. Now, we conduct feasibility studies now after the drilling because now we have already obtained the bore and the coring data, which allows us to evaluate further about the condition of the reservoir. So in this phase, we conduct feasibility studies based on the well discharge data and the analysis of the corings. For this week, we will discuss on the reservoir evaluation based on the processes that occurs in the reservoir that affects boiling or cooling. And for the following week, we will discuss the physical properties obtained from the corings so that we can assess the overall potential that can be served from a geothermal system. Now, the objective of reservoir evaluation or reservoir engineering is for us to describe quantitatively the behavior of the fluids. Here we can understand the processes that occurs in the reservoir, such as boiling and cooling, and we use this information to predict the evolution and the behavior of the reservoir. We also study the reservoir engineering to predict the change in composition because it can affect the reservoir hydrology. The changes in the hydrology can actually determine the successful rate or the sustainability of the geothermal system. We study the reservoir engineering to understand how we can manage the field if we decided to actually exploit and produce energy from the geothermal system. But we need to combine this with the physical measurement and further geochemical data that is obtained from the well discharge of our geothermal area. As mentioned before, one of the reasons that we study reservoir evaluation or we study reservoir engineer is to actually to assess and evaluate whatever processes that occurs in the reservoir that affect the water and the steam composition. I have put together a video that discuss these processes and you can access these videos if you can click it on the link in the description. There's also some of the process that affects the steam composition because if you remember, there are two phases in the reservoir. There is the water and the steam phase. So according to Nicholson, he said that there are 10 processes that affect steam composition. And the main aspect is because of the pressure and temperature differences and the content of gas and the solubility of gas in the vapor phase. Also, the chemistry of the steam and the reaction that occurs in the steam also affects the steam composition. These processes, which affects the steam composition, will later on affect the characteristic of the reservoir because how much steam can be produced and how much composition of a certain minerals is present in the steam can actually determine on which temperature the steam is actually boiling. And why do we need the boiling information? Because we need to understand the exact location or the exact depth of the boiling zone. And now, before we discuss further about the reservoir evaluation, I will introduce you a new concept. This is the concept of mass and heat balance. This is the concept for the second thermodynamics law, which obeys the balance of mass between the one end and the other end. So in reservoir process, it is assumed that there are two phases, which is the vapor and the liquid. And the total fraction of the liquid and vapor is equal to 1. So in order to determine some of the chemical and the physical properties of the reservoir, we can apply the mass and heat balance concept in the equation. And we can also apply this concept in order to assess the total chloride discharge or the total isotope or even the total carbon dissolved in the vapor of the fluid. So the key concept to this mass and heat balance is to make sure that you have an equal equation. So for instance, if you have, like you say, if you have a surface here and you have a reservoir here, so whatever happens in the reservoir will always be equal to the surface. So let's say if you have a chloride of a certain amount of X here, so whatever happens, the chloride should have the same amount on the surface as well. However, there are some adjustments because it is possible during the ascent of the fluid, there might be some change in composition, but then we assess the changes in the composition so we ensure that the concentration between the reservoir and the surface will always be equal at any time. Now, I will give you an example of a mass and heat balance, and later on in this topic, I will also give you an exercise to make sure that you understand the concept of mass and heat balance. So during an adiabatic cooling process, there's a liquid in the reservoir at 265 degrees Celsius, and this fluid is flashed, which means it boils, where when it boils, the liquid actually separates into two phases. They separate into the vapor and the liquid, and it occurs at 100 degrees Celsius at 1 atmospheric pressure. So we need to determine the steam and liquid phase fraction based on this information. You just need to substitute the value based on the previous formula, and this is the value that you obtain after you calculate. And how do you get the number H of each temperature is that you use steam table that you can download it from online. And besides the phase fraction, you can also determine the constituent in the steam, such as chloride. Why do we use chloride? Because chloride is actually a conservative element. It doesn't react. So whatever you have, whatever chloride you have in the reservoir will always be equal to whatever chloride you have in the surface. So here we can also determine the amount of chloride in the reservoir, and we can also determine the chloride in the surface based on this equation here. So please pay attention here. You have to be careful on the fraction because one of the fraction belongs to the steam fraction, the vapor fraction, and the other fraction belongs to the water or the liquid phase. And now I would like to go back to a previous concept that may have been taught in the previous course. This is the geothermometry, where we determine the subsurface temperature based on the chemical composition. You can actually click on the link below in the description because I have put together a video that discusses thoroughly on geothermometry. In geothermometry, we have a solute and the gas geothermometry. We do the solute geothermometry usually during the 3G integration data before drilling. So this is the gas geothermometer. We collect the gas either from the fumaroles or the solfataras. Once you have the well set up, you can actually complete this task in the well discharge. Like let's say you have a well here. You can actually complete your gas sampling in the wells. There will be like a specific box that is actually assigned for collecting gas samples. And these are some of the examples for gas geothermometer. We do analysis on the carbon dioxide, sulfur, and etc. Depends on what gases is more dominant in the sample. And this is the example data type for the gas geothermometer. We obtain the data in fractions and in mole percent. It's different compared to the solute geothermometer, where we actually obtain the data in parts per million or ppm. We have been discussing in the previous course, which is to check the data quality in the form of a charge balance. The ionic balance calculate the sum of anions, which should be equal to the sum of cations in the water composition. So the proper data quality should not exceed plus minus 5%. So this data is good, this data is good, this one's also good. However, if you have these type of data, doesn't mean that you cannot use it, but you have to reassess whether you would include these data in your calculation, such as in the geothermometer or in the fluid type determination. It seems like here one of the ions seem to be more dominant than the other, causing the ionic charge not to be balanced. And this is another concept that you would need to understand to be able to assess the reservoir condition. This is the excess enthalpy, or as usually noted as an HE. So excess enthalpy is produced by the heat flow from rocks that cause differences in enthalpy. It mostly occurs in the liquid dominated system and also the vapor dominated system. We measure the excess enthalpy in the wellhead So if we already have a wellhead from the drilling, we measure the excess enthalpy there. And the excess enthalpy here can help you to infer the equilibrium of gases or the boiling condition in the reservoir. So if you have a well that produces liquid enthalpy, and somehow the enthalpy increases in time, so let's say if you have like initial enthalpy and then somehow at the end the enthalpy is really high, it means that you have an excess enthalpy well, which is good. The excess enthalpy occurs because there is a phase segregation. This means that there is a boiling process occurring in the subsurface, meaning that there are phases that's been separated. So the liquid has been separated into vapor. And also there is somehow an enhanced evaporation due to heat flow. So there is an abundance of heat flow to the reservoir, allowing the fluid in the reservoir zones to somehow boil at a faster rate than before. So this may also occur especially if you have a well, because if you drill a well, the equilibrium or the stability of the reservoir shifted and somehow it becomes more unstable in terms of enthalpy. After discussing some of the concepts that you would need to understand before we actually complete the reservoir engineering or reservoir evaluation, we now can come into discussing the mixing models. This is what we do when we evaluate the condition of the reservoir based on the boiling process. So after considering geothermometers, ionic balance, and then we consider excess enthalpy, total discharge, and the heat and mass balance. And now we would like to discuss the mixing model in order for us to predict whatever processes is actually occurring in the reservoir. So a mixing model, it helps us to understand the process that occurs in the reservoir based on a well-discharged condition. It is very useful, especially in the feasibility studies after drilling, to assess whether the geothermal system that we are working on have a potential in heat flow and also have the proper structural geology to support the sustainability of the system. So here we use fluid chemistry analysis. It's more relatable to fluid chemistry, but somehow it's also closely related to thermodynamics law, which happens to be mass and heat balance. So this is an analogy for the mixing model where we have an iced tea. So we want to assess what factor contributes to the mixing of ice and tea in order for us to create iced tea. So in this case, we have heat and also cooling process, which is we have calories, where eventually the ice will melt and then it will actually dissolve. It will be mixed together with the tea, and eventually it will create iced tea. But this is in a cold or a cooler temperature. In geothermal system, however, we use a hotter temperature, and then the analogy is between the steam and the liquid. And we want to know whatever factor that can contribute to the mixing of steam and liquid so that we can deduce the boiling process and we can locate the exact boiling process for us to target the production zone. There are two types of mixing models that we can usually use when we are assessing the reservoir evaluation. There is the enthalpy chloride diagrams and the enthalpy silica diagrams. Each of these diagrams have their own purpose and have their own use for assessing the geothermal field. So enthalpy chloride is good to understand the hydrology of the geothermal field since it can estimate the reservoir fluid composition. However, the enthalpy silica, it helps you to estimate the temperature when you have a mixing water between the hot water and the cooling water. But this is very limited because in some cases where the reservoir contains high concentration of silica, this diagram will not work as efficiently as you would like. For the first mixing model, I would like to discuss the enthalpy and chloride diagram. So to introduce you with this mixing model, I would like to elaborate on the features that you can see in the diagram. There are at least 7 features that you can see. The first one is the axis, the x and y axis. For the y axis, we have the enthalpy scale, which is notated in the kilojoule per kilogram units. for the y-axis, there is also a secondary scale in temperature. It's notated here. For the x-axis, we have the chloride concentration represented in ppm units. As for the straight line here, it is actually the steam line. Here on this point, we have a steam point, which is the intersection between the enthalpy and the chloride. It is actually standard at 2,700 kilojoules per kilogram. And here along the steam line, we also have the reservoir fluid plot and the HS plot. As for number 5, we have a meteoric water box, which is filled up with meteoric water, and it is low in temperature and also low in chloride because usually rainwater does not contain high chloride. And for number 6, we have a steam heated water box. This is the standard box where we collect the steam. Point number 7 is the boiling spring line, the dash line here. It actually shows you the enthalpy at which water boils at the altitude. So here at the normal altitude, we have water boiling at 100 degrees Celsius and usually at 1 atmospheric pressure condition. Based on the enthalpy chloride diagram, we can see that there is a trend that you could follow in order for you to assess what is actually happening in the reservoir. So if we have the steam line here and somehow the trend or the cluster or the group of fluid relies on this trend here, it means that your system is gaining steam, or you have an increased enthalpy where your chloride content also decreases. And for the second one, if your group of fluid is actually going downwards the steam line, it means that you have steam loss. If it goes upwards along the y-axis, it means that you have a conductive heating. If you go down to along the y-axis, it means that you have a conductive cooling. And if you have a dilution or mixing, it will go inwards into the 0 point. So here, we use the steam line as a base for the evaluation in our reservoir. So we can actually assess what is actually happening in the reservoir, and then we can see whether it's moving upwards, downwards, leftwards, or inwards into the 0 point. If we have differences of enthalpy and chloride according to time, like along a different time, we can actually assess whatever is happening in the reservoir. So let's say if we have well-discharging chemistry and somehow it will dilute over time, or there is no dilution, or there will be dilution with groundwater and etc., you can actually see it based on the trend related here. Based using an enthalpy and chloride diagram, we can also see whatever is happening, whatever is changing in the reservoir. But we need to collect the sample in different time, so then we can assess what is happening over time. This trend can also be used to assess spatial distribution. So not only just for one well, but we can also assess different wells. Let's say if you have one well in the north here, and then you have another well in the south. And we would like to compare the processes that occurs in these well. Let's say here we have a steam loss process, let's say in this point, and then for the second you have a more conductive cooling well. So then we can see that from north to south we have different characteristic of wells, meaning that the system somehow is different from the north to the south. Second mixing model is the enthalpy and silica diagrams. So these diagrams provide a simple technique to estimate the temperature of the hot water in mixed waters. Okay, there are 3 basic assumptions. There should be no loss after heating or mixing. And we need to understand that the solubility of quartz actually controls the silica content, and there should be no deposition or dissolution of silica once the geothermal fluid has left the deep reservoir up to the surface. This method may encounter problem when you come to a very high enthalpy system, maybe above 200 and 300 degrees centigrade, because silica or quartz happen to precipitate very rapidly above this temperature. So what happens if you have a precipitation of quartz? It will actually create solids, and it will create errors when you determine the temperature of the reservoir. Silica enthalpy diagrams, we use these graph here between silica and enthalpy, where the silica is represented in ppm or milligram per kilogram, and the enthalpy is represented in kilojoule per kilogram. So there are three lines of graphs here. We have the MSP line, which represents the meteoric water, hot spring composition, and also the parent fluid temperature. And also you have the maximum steam loss and the no steam loss of the quartz solubility. So as I have mentioned before, the quartz solubility in the fluid depends on the temperature. So as the temperature goes higher, we are more prone to quartz precipitation. However, as the temperature goes down, we are more prone to amorphous silica. Or in other words, we can say the higher the temperature, the more likely for quartz to precipitate. The lower the temperature, the more likely the amorphous silica is more likely to precipitate. So here we have maximum steam loss and no steam loss. This is differed by when you have a maximum steam loss, it means that there is a boiling occurring in the reservoir, meaning that there is flashing, because it somehow separates the liquid and separates the vapor from each other. However, if you have no steam loss, it means that we are dealing with a system that is quite stagnant or even cooling, because apparently the heat is not high enough for the steam and the liquid to separate from each other. So in order to use which one of this line, we need to assess the concentration of the silica and also the temperature in the reservoir. We can usually back calculate the model to determine what is happening in the reservoir. It also occurs that maximum steam loss can also represent the change in the silica content, where usually if we have a maximum steam loss condition, the amount of silica in the reservoir is less than the silica in the surface. So here we have let's say a reservoir and the surface. So the silica content here is much lower than the silica content on the surface. So we can actually deduce what is going on in the reservoir between the changes in silica composition from the reservoir and the silica composition that you took from the wellhead. That concludes our discussion on the reservoir evaluation. Please complete the exercise of the mixing models and also the heat and mass balance for you to understand the concept and actually to apply the concept in assessing reservoir engineering. Thank you for your attention. I will see you in the next class.